In this video, we're going to look at how to create a Sobel edge detection filter for post-processing using HLSL and Unreal Engine 5.3. That way we can have a filter that gets applied to our scene as a post-process to make our scene look like this. You can do similar things to create edge filters or cel-shaded filters or things to make your scene look and render differently using a post-process. First, we'll have to know how to create a post-process volume to add a post-process material to override how our image looks. To do this, we can go up here to this plus and search post-process volume. Now we have a volume box where when you go inside that volume, you can apply adjustments here. But what we're going to do is set it to unbound. So it affects everything. So I'll search unbound and click on this infinite extent unbound. Then this volume or this post-process volume affects everything, not just what's inside the box of it or the bounds of it. The next thing I'm going to do is search material. And then you see these post-process material drop downs here, and you can open this up and add an element and set it to asset reference. Now we can plug a material that's a type of post-process into here to override our scene and what we see. So let's try that out. I'm going to right click and create a new material and call it m_post process. And I'm going to open that up and we're going to change the material. So I'm going to click on the material here and change the material domain to post process. Now we have the emissive color accessible, but now we have to get our rendered image. And a way we can do that is create a node called scene texture. And the scene texture node will fetch different things from our rendered scene. So we can get things like only the metallic pass, only the specular color pass. But we're going to do post-process input 0, which is essentially our render that we normally look at. And if we connect that up and we save that, nothing really changes. It looks the same as it always does. But if we were to invert the image that we're seeing, so if I were to add a 1 minus node and connect our rendered image to that, or scene texture to that, and then connect that to emissive color, it's going to flip the colors of the image that we see. And if I save that now, I can use this material in our post-process volume, in our post-process materials, under our slot here, so I can drag and drop it in, and now you can see our whole frame or our whole render is overridden with these inverted results now. So we just created a very simple post-process volume with a custom override material to control the post-processing of our rendered image. So now you can create all kinds of different filter and effects for your scenes this way. And what we're going to look at now is how we can create in HLSL a Sobel edge detection filter to give us the edges of all these objects and what we see. I'll pretty much apply a edge detection on our whole screen by just going through that image and pretty much doing an edge filter that we're going to make. So let's take a look at how we can code in HLSL a Sobel edge detection filter. So before we start writing our Sobel edge detection filter, we kind of have to understand what it does. Essentially, it's going to loop through all the pixels in the image, sampling a 3x3 pixel grid and filtering out horizontal and vertical edges. So to start doing this, let's go back to our material here that we're currently using. And we're going to be creating a custom node like we've done many times before. We're going to keep this scene texture post-process input. We're going to delete the 1 minus, and we're going to right click and create a custom node. And we can connect that up to our emissive color. And we're going to have to write some code for this. So to see that code a bit better, I'm going to switch to Visual Studio Code. And in our Visual Studio Code or Notepad or whatever you're wanting to use, it doesn't really matter, we're going to have to make the Sobel horizontal filter. So I provide a bit more detail about this in the PDF, but we're going to create pretty much a float called Sobel horizontal. It's going to be 9 different values because it's pretty much going to be a 3x3 grid that goes over all the pixels. This is our center pixel, and it's going to filter over all the pixels and pretty much give more weighting to horizontal pixels and vertical pixels, and use that to produce an edge filter. So this is the horizontal filter, pretty much, and we're going to make it equal more weighting to the left and right pixels, less weighting to the vertical pixels. So if we look at this, these numbers, think of them as describing the strength of the pixels. So it's giving more weight to the left and right side, nothing to the center. And now our vertical filter will look something similar. So we'll do float Sobel vertical, same thing, 9 pixels, 3x3. And it would be something like this. It'd give more weighting to the top and bottom pixels. And there's no, I guess I'd say there's no real rules here. You could change up these numbers to make your own different kinds of filters. So I'm actually going to compress this code a little bit. I'm going to make it into a float too. The X values will store the horizontal filter, the Y values will store the vertical filter. So I'm just going to call it Sobel matrix and make it same thing, 9 pixels, 3x3, and I'll do a float 2. First value is the horizontal filter, second value is the vertical filter. And I'll pretty much type this all the way through. There we go. And now we have our Sobel matrix with X values, or the first value being horizontal, second value being vertical. So just less code we have to write. And now we're going to make a float or a variable to control the intensity of this Sobel edge detection. And I'll just make it 1 by default, but later on we can make control to control that. But I'll just hard code it in for now. And then I'll do a float 2 called gradients. So you can think of the gradient as almost how quickly something changes, how the pixel is changing in different directions. Now we have to loop through all the pixels. So I'm going to go in here and do a for loop. So we're going to do for int I equals 0, and we're going to loop through all 9 of the pixels. That's the 3x3 rows and columns. And then what we're going to do is go in here and specify the rows and columns with variables to make it easier to access. So I'm going to do an int for row and also an integer for columns. And to access the rows, I will do something like equals I divided by 3 because there's 3 rows. And for columns, I modulus 3 since there is going to be 3 columns. And by doing that, that gives us our current row and our current column. Next, we're going to use those rows and columns to get the neighboring pixel offset. So I'm going to create a float for offset X and a float for offset Y. And to get the neighboring pixels, we're going to take the column and we're going to -1 and then divide it by the resolution of our screen. So we're going to have to create a way of getting our screen's resolution into our HLSL code. So for now, I'm just going to call it res, and it'll be a float 2 that contains X value for the resolution in the X value and res Y for the resolution of the Y value. So row -1 divide by res Y. So that'll get us our neighboring pixel offset. And then we're going to use that pixel offset to be able to get the relative direction of those neighboring pixels. So to do this, we'll create a float 2 called offset UV. and that will equal a float 2, where we have the current UV coordinates. So we're going to get the UV coordinates of our screen, and we'll take the UV coordinates x plus our offset x, and then UV coordinates y plus our offset y. And that gets our offset UV, our UV of our kind of neighboring pixel offset applied to the current screen UVs. And then after that, we have to take our image and use this offset UV to essentially grab the pixel from it, and then apply our Sobel matrix to that sampled part of our image, or that sampled UV point of our image. So we're going to do a float sampled intensity, so that's our image, and it's going to be our screen render that we had. When we use that scene texture node, that is what we want to get in here. Now there's a couple ways to access that, and maybe we'll take a little bit of a detour here and just go back to Unreal before we finish our code. So this gets a little bit tricky, because if you have the scene texture post-process input 0 node, and we have our custom node, if we were to do something like create an input called maybe just scene texture, and we connect it to the color here, and then we return that variable, return scene texture. Great, that works. But we can't access its UVs. If I try to access the UV of it, it's going to give me an error. So what we can do instead, and this is a little bit weird because we'll have to have the node connected up, but we don't necessarily need to reference this variable. We can reference directly to this data being connected. And the way we're going to do that is by using a Unreal function for HLSL called scene texture lookup. And this is really just referencing a Unreal function. So it's kind of a little bit specific to Unreal. And we can use that function. And then the benefit of that is we'll be able to specify our UV. So I can specify offset UV. And then a number. And then whether we want MIP mapping enabled. And we don't want to MIP map our image in this case. We don't want to add LODs to our image. And this number will reference exactly to these slots here, where 0 is scene color, 1 is scene depth, 2 is diffuse color. So going all the way down to this post-process input 0, to get access to that data, what we would have to do is reference what number that buffer, that kind of data is in that list. And in this case, if you count those all up, it's 14. So this will allow us to fetch our scene texture post-process, or let's see what it's called, post-process input 0, which is 14th in the list, and specify the UV of what we want to grab, and then also if it has MIP mapping, true or false. So now that we have our sampled intensity variable here, which is the neighboring pixel offsets, so we're sampling the neighboring pixels, we'll now apply our Sobel matrix or our Sobel filter to those pixels. So to do that, we're going to use our gradients variable. We're going to plus and equal, so add our Sobel matrix multiplied by our sampled intensity, which is the sampled neighboring pixels. And that's it. That'll go through all the pixels, apply the Sobel matrix to the neighboring pixels. And now what we have to do is return that gradient as the pixel that it outputs. But first of all, we're going to take that gradient, we're going to multiply it by our intensity, so we have the ability to control it to be stronger or weaker if we want to make the effect not as pronounced. And I'll add a little bit of commenting here. So this is going to multiply intensity of our neighboring pixels by our Sobel matrix, filter, whatever you want to call it. And then here we just pretty much multiply our gradient to be stronger or weaker, but just pretty much apply it by our intensity control. So we have the ability to make it brighter or darker, or stronger or weaker. And then finally, the resulting pixels. So the resulting pixel intensity, or the resulting pixels we get, is going to return. Now we need a way of turning these gradients into a single value. And to do that, we're going to use length gradients. You essentially could return red, green, and blue and just set them all to gradients and get the same result. This is quicker, this is easier. We don't need color because we're just making this as like a black and white Sobel edge filter or edge detection. But if you wanted to have colors, like maybe the edges are red and then different types of things are blue or green, you could return an RGB. So you could return float 3 and set different colors for the edges. But for now, I'm just going to keep it black and white like this. And that pretty much gives us our full code. So now we should be able to use this in Unreal. So if we copy and paste all this, hoping that I have no mistakes in here, and we go into Unreal and we paste it into our custom node. So I'll paste it all in. We're going to get some errors because we need to add some of those variables that we don't have. Like if we go back to our code, we need to get our UVs of our screen. We need to get the resolution of our screen. So we need to feed this input into there. So we need a variable for UV and we need a variable for res. So I'm going to go here to my custom node. I'm going to add those inputs. We'll leave the first input as scene texture. We'll add 2 more. One will be the UV. The last one will be the resolution, RES. Now, how do we get the screen space UVs? There might be a bunch of ways to do this. I'm pretty sure you could do it with the Unreal nodes. But the way I've kind of done it is just using one of, again, Unreal's functions. I find it a little bit easier. So the way we're going to do this is we're going to create a custom node again. And very simply, we're just going to go into the code here and we're going to type return get scene texture. And you have to make sure you spell this exactly with the caps lock and everything. Return get scene texture UV, and then in parentheses, parameters. Like that. And it should return a float 2, not a float 3, because it's returning UVs, X and Y coordinates, or U and V coordinates. So we have to set the output type to float 2. Should go yellow. We'll connect that to our UV. And then to get our resolution, we're going to create a view size node and connect that up to our resolution. Now we get our Sobel edge detection, our Sobel filter here showing up, so that seems it all worked. One thing that I don't think is really an error mistake, but I should correct this. If we go back to our code, we're returning a single value. We're returning length gradients. But currently our custom node here is set to have an output type of float 3, 3 values. Since I'm only returning 1 value, I should set it to float 1. Again, doesn't really make a difference, I don't think. Let's see. Yeah, it looks exactly the same. But it's just good to get into that habit of making sure you set that all correctly. So there's our filter. And if we save this, since we do have it applied in that post-process volume, we now have our filter. Now, look at the weird offset we get here. So that's a little bit of a problem. And this might only be really an issue in the editor in some cases. And you can see with certain resolutions, smaller ones, it doesn't seem to have a problem. One other thing that you should know about the post process materials is there's a very important setting that will determine how your post process material is applied. And if we open up this material and we click on nothing, we can just search through the material here. We can click on the main material here, same thing. And if we scroll down, there's one section called post-process material blendable location. And you can see here, this is where the node is inserted in the post-processing graph. So is the post-processing happening after tone mapping, before translucency, or are you completely replacing the tone mapper? So you can set this, they will look different depending what you set this to. So you might have to do some adjustments, and there's no technically right or wrong thing you should set this to. It really depends on what you're creating or what you're trying to achieve. But by changing that, I could fix this issue. The way to fix this issue, if you have that in the viewport, you could set it to, um, I believe it's after tone mapping. And if we do that, oh, it's before tone mapping. There we go. And then we get our edge filter. And again, if this looks too strong, we could change our intensity control that we coded in. And also, if you have exposure on your camera, or if you go up here and you have some sort of exposure, that is going to affect this as well. So keep in mind when you're doing post-process effects, your exposure of your camera will also affect how it looks. So you might need to change that or change the intensity of your effect or add controls to adjust it better. So that's something you can just keep in mind. But now we have our Sobel edge detection filter done as a post process fully in HLSL. And from this, you can start playing around with that and trying to make your own kind of filters. Even just modifying this code, modifying the colors, you can probably start to create some pretty cool stuff. So give it a try and see what you're able to create. If you enjoyed this video, if you learned something new, don't forget to like, subscribe, check out the Patreon down in the description below. If you are part of the Patreon, you will get access to the PDF for this video that goes over all those steps we covered in a little bit more detail.